Hey there. Today we are going to be doing our first mini lecture on climate change, and this is probably one of the most important threats that mankind has ever faced. I know right now, because we are facing the coronavirus that seems extremely real and scary and immediate threat, and that's very true. But global climate change is also a threat to mankind. It's taken us a while to see the effects that mankind has had on nature and on our climate, but these effects are very real, and the science is undeniable. So I do like to go through quotes from current and previous leaders. We'll talk about climate versus weather and clarify any misconceptions about that. Talk about Earth's atmosphere and temperature, as well as the greenhouse effect and how our climate is naturally controlled by our atmosphere. And we'll talk about the planets in our solar system and how their atmospheres affect their temperature. And your book does an excellent job on this chapter. This is really why I chose your textbook for this chapter. So it should help clarify anything that seems unclear from this lecture or my slides. Then we'll talk about our climate problem and kind of take a look at the evidence that our atmosphere is changing. We'll talk about ice cores and look at, what the greenhouse gases were, 500 to a million years ago. We'll look at that and compare that to the greenhouse gases today. We'll also talk about what natural events affect climate, and then the Keeling curve, and talk about the consequences of rising temperatures as well as discuss solutions. So quotes from previous and current leaders. Of course, Ronald Reagan in 1984 said, preservation of our environment is not a liberal or conservative challenge. It is common sense. And you could take a look at the links for that. Margaret Thatcher surprised me the most about her views on climate change. She said these activities that humans do threaten our atmosphere and the sea around us. That is the scale of these problems. And she goes on, actually, and I have several links by her. She really talks about the evidence that climate change is actually occurring. And this was back in 1989. Okay, this is not 5 years ago. This is not 10 years ago. This is when most of you were still in diapers, maybe not even, no, most of you were not even born yet when she was talking about this. And so anyway, of course, President Obama in 2015 said there's no greater threat to our planet than climate change. And President Trump in 2017 said he was not a believer in climate change. So this is a great video. What's the difference between weather and climate? And I really encourage you to click on this link, watch this video. Climate is long-term weather patterns. So years and years and years of data that can predict weather patterns over time. Weather, on the flip side, is short-term variations in temperature, wind, and precipitation. This time frame includes a much shorter time. This is weeks, days, and maybe even a season. That's weather. Climate is long-term, weather is short-term. So what do you think of this question? This year was colder and wetter than normal in the Bay Area. Climate change must not be happening. Okay, what you've got to think of here, this quote is describing weather, not climate. Okay, so let's look over 10 years and see if this is true, because again, only time will tell you what the climate is really going to be like, not a single season. Again, some more videos on climate change. Totally recommend Bill Nye's videos on climate change. He has several. And I also like the climate scientist from Global Weirding. She is awesome. So climate change occurs when weather patterns change in time. Okay, so suppose a winter in Pennsylvania begins to look like a winter in Florida. Okay, so what's going to happen to our ecosystems? What's going to happen to the animals that live there? What's going to happen to that interrelationship between those organisms? So our air is composed of 78% nitrogen, 21% oxygen, 1% argon, carbon dioxide, and some other gases like water vapor. So water vapor ranges from 0 to 4%. Nitrogen and oxygen are transparent to visible sunlight, and the sun penetrates the atmosphere like a clear glass window. Okay, so it just goes straight through that clear glass window and hits the planet. Some of that bounces off clouds, right? Okay, so some of the light is reflected back towards the sky, especially when the sun hits something that has high reflectivity, so it has high albedo, such as snow. Okay, so things that have low reflectivity, think of your black asphalt in the summertime. Okay, things with low albedo are going to absorb that sunlight and or absorb that radiation from the sun and convert that light into infrared radiation. Okay, so again, because most of the light is absorbed by the Earth's surface, and the energy is slowly re-emitted through infrared radiation. Okay, and that's also what we call heat energy. Um, you can still feel that heat radiating from a parking lot on a hot day. So most of that infrared radiation does not pass back through the atmosphere. Infrared radiation loves to get trapped and absorbed by clouds and gases such as CO2 and water vapor. And this helps create a warm blanket on our planet. Now we do need some of this, okay? This is a good thing. This is the greenhouse effect. Okay, so we want some of that infrared radiation being trapped by our atmosphere and radiating that heat back to the earth. Okay, so we do want some greenhouse effect. Again, albedo refers to the amount of reflectivity that a substance has. Snow and ice have high albedo and reflect light back to the atmosphere. Okay, and it's also why you may get burned under your chin if you're skiing or snowboarding. Okay, so that sunlight bounces back off the snow and hits your chin, and you can get a sunburn, right? So, and some of that, some of that light is UV radiation, right? And that bounces off the snow, and it can, again, give you a sunburn. All right, asphalt, black pavement is not going to have a high albedo. It has a very low albedo. It absorbs the light energy, okay, and it converts that light energy into infrared radiation. The infrared radiation is what we feel is heat. So the greenhouse effect, again, without the atmosphere trapping that infrared radiation, the Earth's temperature would be way too cold to support life. So it would only be 21 degrees Fahrenheit. So that is really, really cold, right? The greenhouse effect makes our current temperature around 57 degrees Fahrenheit, although now it's getting warmer because we are experiencing climate change. 57 degrees Fahrenheit is critical for liquid water and life on Earth. 21 degrees, we'd be a frozen ball of ice. Again, we see the sun, light energy coming to the planet. Again, about half of that solar radiation is absorbed by the Earth's surface and helps warm it. Infrared radiation is emitted from the Earth's surface, and that infrared radiation is trapped by our atmosphere and clouds. So if the sun was the only variable controlling temperature, which of the four planets would be the hottest? It would be Mercury, right? That one's the closest to the sun. Venus is second in line, Earth's third, Mars is fourth, and then these other planets, they're too far from the sun, right? Okay, so Mercury's average temperature is 167 degrees Celsius or 332 degrees Fahrenheit. However, Venus, who's number 2 in line, average surface temperature is 867 degrees Fahrenheit, and that's as hot as a traditional wood-fired pizza oven. It's 2.8 times hotter than Mercury. Okay, Earth's temperature now is 59 degrees Fahrenheit, and our planet is just right for us. Okay, Mars' average surface temperature is quite a bit colder, and it's negative 65 degrees Celsius or negative 85 degrees Fahrenheit. So Venus is hotter than heck, right? And really the differences in temperature between Earth, Mars, and Venus depends on their atmosphere, right? So Venus has a very thick atmosphere, so it contains 96% CO2, and again, the average temperature is 867 degrees Fahrenheit or 420 degrees Celsius. Now, the Earth's atmosphere contains 0.03% CO2 in our atmosphere. Okay, so that's in comparison to Venus. It's a thinner atmosphere, right? So the average temperature is, about 59 degrees Fahrenheit or 15 degrees centigrade. Mars has an extremely thin atmosphere. Almost all the carbon dioxide of Mars is actually in the ground, okay? And the average temperature is negative 50 degrees Celsius. So Earth's atmosphere is made of CO2, but it is only 1% as dense as the Earth's, and it gives it very little heat trapping capacity. Venus's atmosphere, again, is almost entirely carbon dioxide, but is 92 times denser than the Earth's atmosphere. Therefore, it traps a huge amount of heat energy and it produces a massive greenhouse effect. So I hope our goal or humanity's goal is not to become more like Venus. Okay, we don't need to have so much CO2 in our atmosphere that we end up being like Venus. Okay, so scientists have known about the greenhouse effect for a while, and they also understood infrared radiation for a while. And so I would encourage you to look at the experiments by Herschel, and there's some other experiments here as well. Tyndall also did some experiments, and he hypothesized that water vapor, carbon dioxide, nitrous oxide were strong absorbers of infrared radiation, and he set up experiments showing that was true. And he asserted that the Earth would actually be a frozen world without these gases. This is the late 1800s, early 1900s, so not very recent. Arrhenius is considered to be the founder of climate science. He predicted a doubling or tripling of atmospheric CO2 would raise temperatures 5 to 9 degrees Celsius. His work was published in 1896. So it's kind of incredible that we haven't listened to these people sooner. Okay. So we're just going to briefly talk about how solar energy and the atmosphere naturally warms our planet. Okay, so gases that have 3 or more atoms will absorb heat or infrared radiation. So water vapor is very good at doing that. Carbon dioxide, you guys know that. Methane, nitrous oxide. You guys learned about nitrous oxide in the air pollution chapter. HFCs, these are in air conditioning units now. Also, chlorofluorocarbons, which have been banned. Now, sulfur oxides actually have a cooling effect, as well as aerosols from volcanic eruptions. And we know that aerosols from volcanic eruptions often include sulfur oxides. So if we look at this table, this is from your book, it shows global warming potentials of 4 greenhouse gases. So carbon dioxide, we know, has a good ability to warm the atmosphere, but compared to some of these other compounds, it's not quite as potent. So methane is very, very potent. Over 100 years, methane is 28 times more potent than CO2. Now let's look at nitrous oxide. Nitrous oxide is 265 times more potent than CO2. And HFCs, 12,400 times more potent than CO2. So these other gases will also warm the planet as well. I want to point out that carbon dioxide doesn't disappear after 100 years. It would still be in our atmosphere after 1,000 years. So it's very, very hard to get it out of the atmosphere, especially if we don't change our habits. But if we have things that can bind to carbon dioxide, like plants, we can draw CO2 out of the atmosphere. Again, we're going to need a lot of plants to help with our climate problem, and that's not going to be enough to solve it. I mean, certainly planting trees, that's absolutely a worthwhile endeavor. It's good for the planet, it's good for your local environment, it's good for, organisms, in your neighborhood. I really would encourage you to plant things, plant trees, plant flowers. All these things help bind CO2, and they provide homes and pollen for insects and other organisms. So really, really important, and certainly is not going to hurt, our problem with climate change. Okay, planting trees is excellent way to help, reduce, at least, make some impact. You're not going to make a huge impact, massive impact to completely reverse climate change, but I'm saying that planting trees is an important aspect. Also, we need to protect the forests that we have. We need to protect our rainforests. We need to protect our boreal forests. Those are important carbon sinks, and if we lose those, that unfortunately ends up being a positive feedback loop for climate change. Okay, so what's our climate problem? The balance of incoming energy and outgoing energy determines the Earth's temperature. So before the 1800s, we were not acquiring more heat. The Earth was in balance. But currently, we are slowing our rate of heat loss. We are slowing this. We're slowing the rate of heat loss, increasing the heat storage in our greenhouse by adding more carbon dioxide, methane, other gases like nitrous oxide, HFCs, right, into our atmosphere. So you can sort of think of carbon dioxide and other greenhouse gases as like a blanket around our planet. And what we're doing is adding another blanket as we add more greenhouse gases to the atmosphere. And that is just going to make our planet warmer. It's going to trap more infrared radiation, and and we're not going to be able to cool off as quickly. Okay. All right, so this leads into the idea of radiative forcing, and I would totally encourage you to watch this video as well on radiative forcing. Radiative forcing examines how gases affect the planet's heat gain or loss. Okay, so we know that carbon dioxide, so we're looking at radiative forcing on the x-axis here, okay, and that's relative to 1750 watts per meter squared or per cubic meter. Okay, so if we look at carbon dioxide, it has, let's see, about 1.5 positive factor in radiative forcing. Methane has looks like about 1.25, 1.5. In the troposphere, our ozone is going to be about, it definitely has some radiative forcing, but not as much as carbon dioxide or methane. So it looks like about, I don't know, 0.5 or 0.4 to 0.5 positive units of radiative forcing. Soot on snow also has positive radiative forcing. Again, radiative forcing means that it's going to warm the planet. Now, negative radiative forcing, like aerosols from volcanic eruptions, those are going to have a cooling effect. Okay, so aerosols, sulfur oxides, volcanic eruptions. Okay, so about -1 radiative forcing, so that has a cooling effect. Total radiative forcing for man is about 2.25. Okay, so we're definitely warming the planet with these greenhouse gases. Okay, so the Earth is now experiencing a positive thermal forcing of 2.3 watts per meter squared, and that's more thermal energy than it is emitting into space. So this is equivalent to 200 that incandescent bulbs, that's the old-fashioned light bulbs, which got pretty warm, across a football field. And realize these football fields are all across the planet. So if you think of it like that, that's a lot. That's a lot of heat that we're trapping. Okay, so that's incredible. Okay, so again, in contrast, pre-industrial Earth was emitting as much radiation as it was receiving. Okay, so let's take a break here and I will talk more about what levels are greenhouse gases today in mini lecture 2. And that's all for now.